Afternoon, guys. I hope you're doing well. So we're going to get into the next lecture, which is the redox lecture. This lecture number 7. Redox is, in my opinion, a very fun topic. I love this topic. So we'll talk first about what a redox reaction is defined as, and then what an activity series is, and then we'll talk about how we balance redox reactions, because that's something we haven't talked about before. So let's go ahead and get into this. I do not have a review today. Didn't do one this time. Not sure why, but anyway, let's get into our new topic. So a redox reaction is actually made of two components. So one of those components is an oxidation. In the oxidation, Ca is oxidized, it loses electrons. O2 is reduced, it gains electrons. Okay? And so that oxidation and reduction have to occur together. I can't lose an electron and have it go nowhere. And I can't gain an electron and have it not come from somewhere. So that transfer of electrons has to be between two species, one oxidized, one reduced. And so we often refer to these, and I always refer to this as redox. In that one word, we know that we're talking about both processes, okay? So that's what we're talking about here, is transferring electrons between two different species. Now, this is a different type of reaction than what we've talked about in the past. So we're not just trading cations and anions, changing where we're located. We're actually talking about moving electrons. And this is a different kind of process. Now, this is something that happens a lot in organic chemistry, but it's not something that we typically have talked about so far. So that's the beginning of this. Now, we can assign something called an oxidation or an oxidation state. This helps us to understand if this species has gained electrons or lost electrons, or if it's changed at all. We do that by assigning oxidation numbers. If the oxidation number increases for an element, that element is oxidized, it has lost electrons. Charge goes up. If the oxidation number decreases for an element, that element is reduced. Charge has gone down, so we gained electrons. So that's the process that we're talking about there. So let's talk about how we do oxidation states. That'll be a fun discussion, right? Now, there are a bunch of rules here, and I'm going to read them to you, and then we're going to talk about exactly what we mean by each of these things. The sum of the oxidation numbers in a neutral compound is 0. The sum of the oxidation numbers in a polyatomic ion is the charge of the ion. Elements in their elemental form have an oxidation number of 0. The oxidation number of a monoatomic ion is the same as its charge. Oxygen has an oxidation number of -2, except in the peroxide ion, in which it has an oxidation number of -1. Hydrogen is -1 when bound to a metal, +1 when bounded to a nonmetal. Fluorine always has an oxidation number of -1. The other halogens have an oxidation of -1 when they are negative. They can have positive oxidation numbers, most notably in oxyanions. Oxidation numbers can be fractions as well as integer values. Okay, that's a lot of rules. And I know it's a lot of rules. But they're things that we need to be able to work with in a practical sense to figure out what these oxidation states are. So let's see what that looks like. And hopefully that will help you to make sense of this. Now, the first thing I'm going to do is try and tone down those words. So I'm going to give you a synopsis of what we talked about. 4 elements, as they appear in nature, their oxidation state is 0. So sodium being a metal, that's a 0. Oxygen, O2, is going to be a 0. Cl occurs naturally as Cl2, so that's going to be a 0. Okay, so however we find them in nature, they will have an oxidation state of 0. If they're a monoatomic ion, so they're made out of one species, so like a sodium, and it's an ion, so it's lost or gained in electrons, like an Na becomes an Na+. Actually, I should have written this down before. Kind of thing. So if it's an Na+, then its oxidation number is equal to the charge. So here, number equals the charge. F is always -1. F, always -1. O is -2, unless it's in a peroxide. Now, peroxide, we most often see this as hydrogen peroxide, H2O2. Okay, and so there's one oxygen per hydrogen that's present. It doesn't have to be H2O2. We can see things like Na2O2. There are lots of different peroxides. So when we have the same number of the other thing as we have oxygen, so usually a metal that it's bound to, that oxidation state is -1 rather than -2. Okay. Hydrogen is almost always +1 unless it's bound to a metal. So if we were talking about something like NaH, the Na is the positive, the H is the negative. And so the oxidation number on that is equal to the charge, which is -1 there, unlike it normally is. And the sum of the oxidation numbers equals the overall charge. So if it's a compound, then the overall, in that compound, there is no charge. Then the oxidation states of all the species in that compound have to equal 0. And that would be something like, if we're talking about H3PO4. So the sum of the oxidation numbers here equals 0. If we're talking about something like the PO4 3- ion, sum of those oxidation numbers has to be equal to -3, because we have to get that charge from somewhere. So that's where that comes in. Okay. So those are the rules that we're going to be looking at when we're talking about these next couple of things. Now, for my life, so that I can refer to those while we're talking about the next set, we'll keep those rules up. So you're going to be referring to the rules. I'm not going to be able to switch back and forth on my screen very easily. So let's go see what we're talking about. So I would like to predict the oxidation numbers for all of these things. So O2. Well, oxygen in its elemental state is O2, so that's a 0. H2O2. So this is a peroxide. That means the H is a +1 and the oxygen is a -1. Okay. When we talk about NaF, we know that F is always -1. And I like to write them in the order that they appear in the compound. It just helps my head. It helps me keep track. So the F is always -1, and that means that Na has to be +1, which makes sense to us because it's a positive charge. Okay. Now, if we want to talk about the oxidation numbers of everything in this H3PO4, okay, awesome. Now I know that when I talk about H3PO4, I'm going to have an H, a P, and an O. There's 3 hydrogens, 1 phosphorus, and 4 oxygens. Now, I know that oxygen has an oxidation number of -2. That means that the overall oxidation for that is -8. Okay, 4 times -2, -8. And I know that in this thing, all of those numbers have to equal 0 because it has no net charge. So I have to get to 0. I know that the H is going to be a +1. And that means that this is going to be 3. And so if I want to take 3, add it to something, and get a +8, so that then when we subtract the 8, it goes away, then I have to make this 5. Okay, and that means this has to be a +5. Okay, we call that process right there determination of oxidation number by inspection. And this is something you probably did in 110. We were supposed to find out what the charge was by inspection. Okay, so this is the same kind of process here. We're not doing much of anything different. So the H3PO4, that's how I get all of those numbers. I'm going to talk about Fe2, Cr2O7, 3 down here. Now, I have an Fe, and I have this Cr2O7. And I can see from this formula that the iron has a +3 charge. And the reason for that is because I know that the Cr2O7 is a polyatomic ion that has a -2 charge. So this overall is -2. And so if that's -2, then that's how I get this Fe2 over here, that 2 is because of the charge that was on this ion. So the Cr2O72 minus, the 2 comes over here, and the Fe has to be a 3 plus because we have 3 of them. So that's how we know that that's what it is. Okay, we try that when we do this. Okay? So it's an Fe3 plus. Okay, awesome. If that's an Fe3 plus, and I have 2 of those, that means this is overall plus 6. This Cr2O7 times 3 is going to give me a negative 6, and so that part is equal to 0. But now I have to determine what the Cr2O7 is going to look like. So I know that there's a Cr. I know that there are 2 of them. I know that there's a 7, or oxygen, there are 7 of them. And that when I'm done, this is going to be a minus 2. So that ion has to be a minus 2. Okay, awesome. Well, I know that oxygen is negative 2, so I'm going to start with that. So negative 2, that means this is negative 14. In order for that math to work, I need to end up with negative or positive 12 from the chromium, right? Positive 12, but there are 2 of them. So that 12 gets divided. So we end up with 12, 2, which is a plus 6. Okay. That's the math that I had to do to get that number. Right. So that's how I end up with the plus 6 for the chromium and the negative 2 for the oxygen. Yay. Awesome. That was fun. Let's talk about Hg2Cl2 here. And I'm going to go ahead and write the next one, the HgCl2. These are very similar things, but they're not exactly the same. One of them has Hg2Cl2, and the other one has HgCl2. And we know that oxygen is always minus 1, right? So if this is a minus 1, and there are 2 of them, that's a minus 2 that comes from there. And so because this is 0, this has to be a plus 2. Since this is minus 2 from 2 of them, negative 1 charge, this Hg2 has to be a total 2 plus. And so that particular species, Hg2 2 plus, is what I'm looking at. That's the ion in question. And its oxidation state is 2 plus. Okay. So that's those 2. Oh, awesome. That was fun. NaH. Okay, well, we said that hydrogen was plus 1 unless it was bound to a metal. He is bound to a metal here. So that H here is going to be a negative 1. That means my Na, because that whole thing is 0, has to be a plus 1, which makes sense to me because that should be his charge. If I have a BaO2, one Ba, there are 2 oxygens. I know that the oxygen is minus 2. That gives me a negative 4 for that. The overall charge is 0. Okay, I have 0 on that particular compound. And I have 1 Ba, so in order to make that math work, that has to be a plus 4. So that's a plus 4 there. We have one more that we need to talk about, which is this MONO3. So the 3 oxygens, 1 MO. This is overall a 0. I know that those oxygens are minus 2, so that gives me a minus 6 there. And if that's a minus 6, then I know that this other one has to be a plus 6 to make that math work. Okay. So those are the oxidation states that I have predicted for each of these compounds and why I said what I said. Okay. So hopefully that's helpful to you. That is something that you will probably need to do when you may get asked what an oxidation number is for a particular compound. Okay? So hopefully there are no questions about that. Now, a species of oxidized, but it loses electrons. Zinc loses 2 electrons, forming the Zn2 plus ion. So we go from zinc solid to Zn2 plus, so 0 to 2. The species is reduced when it gains electrons. H plus gains an electron forming H2, and there are 2 of them, so that's a 2-electron process. Oxidizing agent causes something else to be oxidized. A reducing agent causes something else to be reduced. So my oxidizing agent is the H plus because it causes oxidation in the zinc. My reducing agent is Zn because it causes reduction in the Z. Okay, so I was walking through it in my head. Sorry, it's a very convoluted process in my head, so I'm sorry. So that's what we're talking about for that. Now, how do I know all of this stuff? Well, I listed it before. You may have seen before LEO GER. I've also seen this as OIL and RIG. These are both mnemonics to help me remember stuff. And I actually go through these in my head when I'm trying to do this. Lose electrons, oxidize. You'll hear me say it every time. Lose electrons, oxidize. Gain electrons, reduce. So I'm looking at this and you go, okay, H plus to H2, I've gain electron, reduce. So that is the one that's reduced. And then my Zn, okay, we have lost electrons, that's oxidized. Okay, so that's how I do that. Now the other one is oil rig. So Leo, the line goes GER. Leo, lose electrons, oxidize. GER, gain electron, reduce. I've also seen this as oil rig. So oxidation is loss, reduction is gain, is what that stands for. Whichever one works for you, great. I'm very much a fan of the line, so I usually go with that. Okay, and remember, when we talk about oxidizing agents and reducing agents, at least in my head, these are backwards. Okay, so an oxidizing agent causes oxidation in something else. Okay, so whatever is reduced is the oxidizing. A reducing agent causes reduction in something else. So it is the thing that's oxidized. Okay, so since it causes it in something else, then I can back up and say, oh, okay, so it itself is. And that's how I do it in my head. Okay? So hopefully that's helpful. Go awesome. Let's do a little practice. Identify what is being oxidized, what is being reduced, what is the oxidizing agent, and what is the reducing agent. Let me show you how I do this. All right. So I know that we're talking about chromium on the reactant side, chromium on the product side. And say, okay, those two are connected. They're related to each other. I go from Cr plus to Cr3 plus. So 2 electrons were transferred in that process, and they were lost. So lose electron, reduce. Cool. Now Sn4 plus goes to Sn2 plus. So that's a 2 electron process. And we go from 4 plus to 2 plus, so we gain electrons because the charge goes down. So that's a gain electron reduced. I know that's a little hard to see because it's written over other stuff, but that's how that works in my head. And you'll see me do this all the time because that's how I do it. Okay, so we take our Hg2 plus goes to Hg. We need, and it's Hg2. We have to take 2 electrons to be able to do that. And of course, he had to gain those, so that's a gain electron reduced. We go from Fe to Fe3 plus. So that's a 3 electron process. And that 3 electron process, we lost those three electrons. So that's lose electrons, oxidize. Chaos. One other thing, sorry. So the reducing agent. First one, oxidizing agent. So, gain electron reduced. So, it itself is reduced. It causes oxidation in something else. So, my oxidizing agent is this Sn4 plus. My Cr plus is lose electrons, oxidized. So, since it's oxidized, it's causing reduction in something else. So, that's my Cr plus. And again, convoluted as it is, that's how my head does it. All right. Let's talk about it for this second set. So reducing agent, oxidizing agent. So reducing agent. Well, let's talk about gain electrons reduced. Hg2 plus gained electrons. If it gained electrons and was reduced, it's the oxidizing agent. So Hg2 plus. When we talk about the Fe, it lost electrons. That means it was oxidized. That means it caused reduction in something else. So that's my Fe. Okay? So that's, again, the logic that goes in my head is to walk through that. Now here we have an As solid going to this AsCl. And the Cl2 minus going to the AsCl3. Now, we have to look at, so this is a 0, right? This one's a 0. This one's a 0. In the AsCl3, I know that Cl is a -1. And I know that the As then has to be a 3 plus, because that's why I have 3 of the chlorines. Okay, so that balancing gives me that. So my chlorine has gone from 0 to 3 plus. It went up. It lost 3 electrons. If it lost electrons, it was oxidized. Therefore, it's a reducing agent. And that's the C2. Oxidizing agent is that As. So again, As goes from 0. Wait, what? Oh, garbage. I did that backwards. Sorry. Let's back that up. I apologize. I paired them incorrectly when I attempted to do this. So, As to As, we go from 0 to 3 plus. So that one is the lose electrons oxidized. And it's a 3 electron process. I had it identified wrong on the reactant side. So lose electrons oxidized causes reduction in something else, so that's As. The oxidizing agent, we go from 0 to -1. There are 3 of them. That's gain electron reduced. So for that one process. Okay. And so the thing that does that is the Cl2. Okay. Well, awesome. Okay. Make sure you've got everything paired the way it's supposed to be. We have to compare the same species on both sides. Because what I had written the first time was to go from the 0 on the As to the 3 plus on the Cl. I was trying to do it that way. So that didn't work. Okay, so there's that. Now, this should be an I2 like that. And identify if the material here is being oxidized or reduced. Would you call it an oxidizing or reducing agent? So here I go from -1 to 0. That means I have lost electrons. Oxidized. And then, or it's a reducing agent. Okay, well, that's awesome. Now let's talk about this other thing. So we have our Mn, and it's an O4 minus. So I know that we end up with a -1. I have oxygen. There are 4 of them. Each one is a -2. That gives me -8. And so my Mn, to make that math work, since there's only 1 of them, has to be a +7. This is +7, and over here it's 2 plus. So we have gained. So that's reduced, and therefore it's an oxidizing agent. And of course, that process to go from +7 to +5 is a 5 electron process. Now, notice I started talking about how many electrons were transferred and things like that. We're going to get to that. It will come. What I wanted to do here was to show you that we can look at one individual species and not an entire reaction. Now, why do we do that? Well, that's an interesting question, because I told you that we couldn't have an oxidation without a reduction. We can't have a reduction without an oxidation. But we often see these tabulated by themselves. So they'll appear in tables by themselves. So they're not, paired with something else. We talk about standard reduction potentials. Okay, so they're always written as reducing reduction reactions. So they're gaining electrons. Right? That's how they're written. And we call those half reactions. because I only have the reduction. So I'm looking at a half reaction, and that's because it's only the reduction. We have no oxidation. Okay? So we'll start to get into what all of that looks like and what that means and what we can do with that as we go through this. Okay. But before we do that, I want to talk about one other thing. This is an activity series. So you were introduced to this in 110, and it says elements higher on the activity series are more reactive. They are more likely to exist as ions. So the higher up on this table you are, the more likely you are to be an Li+, so on that product side. Li is the strongest reducing agent, will reduce any ion below it on the right. Now remember, these are all written as reductions. So if it's going to react with something below it on the table, we have to talk about it reacting with a product, not another reactant, okay? Because that's the way it would be in oxidation, is to reverse it. Oh, did I just say that? I did. So my reductions are always lose electrons, oxidize, gain electrons, reduce. Okay, so the one is the reverse of the other. So that's what we're talking about. So Li is the strongest reducing agent, causes reduction in any ion on the thing below it. And these are actually written as oxidations. The activity series is like, just forget that. So these are oxidations as they're written. So electrons oxidize. Okay, so Li is the strongest reducing agent, causes reduction in things on the other side. If we want to rank iron, magnesium, and lead. Lead is right here. Iron is right there. And Mg is right here. Okay. If I want to rank them in terms of reducing strength, Mg is the highest in the table, so it's going to be Mg. Greater than Fe is the next thing, the thing below it. And then Pb is the last one. So that's my rank in terms of where they are on the table, higher up to lowest down. And then it says, would SN be able to produce H2 in an acidic solution? I have to find SN. So SN is right there. And it says over here, reacts with acids to produce H2. And the question says, would SN be able to produce H2 in an acidic solution? The answer to that is yes. Okay. So, yes. And that's because of where it is in the table. So it says reacts with acids to produce H2. Go, awesome. So that's one use of an activity series. Couple. Let's see what else we've got. Tell me the three materials most likely to be ions on the table. Most likely. Now, we said that the things that are most likely to be ions are the ones that are highest in the table. So we're talking about these three being the most likely to be ions. What are the three items least likely to be ions on the table? Sorry, lost our connection. Give me 2 seconds. Hopefully I can get it back. Come on. Work with me here. Okay. Take a brief pause and close this. Hopefully restarting it will help. When in doubt, always restart. Screen share. Oh, okay. Take a minute to actually try to share. Yay! So 3 items are least likely to be ions in the table. Those are our least reactive. So these are going to be these 3 down here. Can Mg react with water to produce hydrogen gas? I see Mg right here. And that is in the part that says react with steam to produce H2. Can it react with water? Yeah, actually it can. So so we've got a couple of things. So we've got cold water above it. So it can't react with cold water to produce H2. It's too far down. It has to be hot water. So with hot water, yes. So the steam will do it. The water won't. Okay. It's hot, not, sorry. Hot water. Could lead react with nitric acid to produce hydrogen gas? So lead is down here. React with nitric acid to produce hydrogen gas. Well, lead is in the section that says reacts with acid to produce H2. So if it's going to react with nitric acid, that's a yes. Can Ag react with anything to produce hydrogen gas? There's Ag in my table. It's a good question. And he's right here. Can he react with anything to produce hydrogen gas? No. Does not react with water or acids to produce hydrogen gas. So the answer there is no. Can barium react with anything to produce hydrogen gas? Well, barium is up here. He's one of my most reactive. And if I look, it says he's in the react with cold water to produce H2. But if he can do it in cold water, he can also do it in hot water. He can do it with acids. Okay, so all of those things will apply to that one. Okay? And that's how it works. Another thing that we can look at with the activity series. Dun dun dun. Okay. 2 seconds. I'm going to go ahead and pause here. I'm going to stop this recording and get us set up for the next one. Thanks for being with me, and I will get this stopped and get back to you soon. Thanks, guys.